Hello everybody, welcome to the Ultimate Physics channel. The topic of this video is solving problems on the photoelectric effect. This video is part 1 of the solving problems on the photoelectric effect two-part video series. Let's first quickly recap the essential concepts of the photoelectric effect so that we can solve the problems quickly. The energy of the photon. The energy of the photon that makes a radiation frequency nu, let's say, is E is equal to h nu, that is Planck constant times the frequency. That is the total energy of a single photon. This is also called as the quantum of radiation from Planck's quantum theory of black body radiation. This was originally conceived. In terms of wavelength lambda of the radiation, this can be written as E is equal to h times c over lambda, where c is the speed of light, h is the Planck's constant, lambda is the wavelength of the radiation under consideration. The momentum of the photon is given by P is equal to E over c. This is from special relativity. We can write energy over c as equivalent to the momentum. Therefore, if we substitute P is equal to hc over lambda from the previous divided by c again, we get P is equal to h over lambda. That gives us the momentum of the photon. Since photons travel with the speed of light, they are massless and their rest energy also happens to be zero. The photon energy in terms of its momentum can therefore be of course written based on this as E is equal to Pc. Einstein's famous photoelectric equation is giving us an expression for the maximum kinetic energy of the emitted photoelectrons in the photoelectric effect. The maximum kinetic energy, that this is the maximum energy the photoelectrons can have, is given by h nu minus phi. This is the single expression that is called as the photoelectric equation. Here, the term phi represents the photoelectric work function of the metal. The maximum kinetic energy is related to the stopping potential Vs in photoelectric effect as EV suffix s is equal to h nu minus phi. So we have gone from Ke max, that is the maximum kinetic energy of the photoelectron, is equal to h nu minus phi. From there we have come here. So we understand that Ke max can be replaced by this term E times V suffix s, where E is the energy, where E is the electric charge and V suffix s is the stopping potential. That is the potential that stops even the most energetic photoelectron from reaching the anode. The work function is related to the threshold frequency required for the photoelectric effect. This relation is work function phi is equal to h times nu dh. Nu dh is the threshold frequency, that is the minimum frequency that is required for the incident light. When it hits a metal surface, that should be the minimum frequency that is required for the incident light, that is nu dh. If the incident light has a frequency less than nu dh, then no photoelectric effect takes place, right? Therefore, the work function is the minimum energy that is required to release an electron from the metal surface. Therefore, the photoelectric equation can also be written in terms of whatever we discussed as the electron charge E times Vs, that is V suffix s, is equal to h nu minus h nu th. Instead of phi here, we have put h nu dh, that is h Planck's constant h times the threshold uh, frequency, and this can again be equated to the Planck's constant is taken out as a common factor h times nu minus nu dh. So these are the expressions that we would need while solving the problems on photoelectric effect. It is also important to recollect the values for some of these constants readily. If you remember these constants, it will be very useful to solve problems quickly. Planck's constant, of course, h is equal to 6.63 times 10 power minus 24 joule second. Speed of light c is equal to 3 times 10 power 8 meters per second. Charge of an electron is E is equal to 1.6. We are taking only one decimal here. We can take 1.602 also, depending on the accuracy that is needed in a problem. So here it is 1.6 times 10 power minus 19 coulomb. And then 1 electron volt is equal to 1.6 times 10 power minus 19 joules. This is the conversion for energy in electron volt units to joule units. Now let's proceed on to do some problems on the photoelectric effect. The first problem, the frequency of an FM radio station, that is a radio station which uses frequency modulated waves for broadcast and transmission, that is FM radio station, is broadcasting at 98.1 megahertz frequency. The power of its signal is given as 50,000 watts. What is its rate of emission of photons? So that means we have to calculate the rate of emission, that is how many photons are emitted in such a signal per second. That is what we mean by rate of emission of photons. So it's a simple problem we can easily solve by taking the total energy of the signal, or the power rather here in this case, and calculating the energy of each photon based on the frequency value that is provided to us, and then based on these two numbers we can calculate the number of photons that are emitted per second, or number of photons that are contained in such a signal, frequency modulated electromagnetic radiation, right? So here we first calculate the energy of a photon. Energy of the photon is, in this case, let's say E is equal to h times nu, where h is the Planck's constant, so I'm going to directly substitute 6.63 times 10 power minus 34 joule second is the unit, and multiply by the frequency, which is 98.1 megahertz. So I have to multiply mega for mega 10 power 6, and for hertz the unit is per second, right? So if you do the math here, we get about 650 times 10 power minus 28 joule. and we can write that as 6.5 into 10 power minus 26, right? So this is the energy of each photon in this radiation. And now we have to calculate the number of photons, number of photons that are present in this signal per second, because our units here are in power units, right? So we can write that as total energy, which is 50,000 uh, joule per second. That is a unit. 1 watt is, here it's given in watts, right? So 1 watt is 1 joule per second. So we have 50,000 watts, so 50,000 joules per second over the energy of each photon, that is, we have calculated here that as 6.5 times 10 power minus 26. So that is this 10 power minus 26 goes to the numerator as 10 power 26. There is a 10 power, let's say 3 we can take out, so the answer has to be in 10 power plus 29, and then this is 50 over 6.5. If we do the calculation, we would get about 7.7 to the first decimal rounding off, and therefore we get these many photons per second in this signal. So that is the answer. So that is the answer to this question. Let's move on to the next one. Calculate the threshold frequency for lithium, whose work function is 2.93 eV. If the wavelength of the incident light is 380 nanometers, what is the stopping potential? So for lithium, the work function is given, that is the phi value is given as 2.93 eV. Let's call that phi suffix lithium. And they're asking us to calculate the threshold frequency, which is nu th. That is the notation that we are using, is what? So we know that this is directly connected very simply. But then what is being asked is the wavelength of the incident radiation is 380 nanometers. So then under that condition, what is the stopping potential Vs? That is also asked. So these are the two things. First one is straightforward. That is, we know that the work function phi is relative to the threshold frequency as h times nu dh, right? So we want nu dh, nu threshold, dh is for threshold I'm using. So we say phi over h. Our phi is in electron volt units, so 2.93 eV. I have to convert into joules, so we know that 1 eV is approximately 1.6 times 10 power minus 19 joule. So I'm going to put that number here, 1.6 times 10 power minus 19 joules. Now the energy units have been converted, or the work function units have been converted into joule units. This over the Planck's constant 6.63 times 10 power minus 34. The resulting frequency is per second units, so that is hertz. So nu suffix th is equal to, if you work out these numbers here, you're getting the threshold frequency as 7.1 times 10 power 40 hertz. Of course, here the units, these rules can cancel, so this is per second, so 1 hertz is, so we are writing it as hertz here for frequency. The second part is the stopping potential calculation, and we know that From the photoelectric equation, the maximum kinetic energy Ke max is h times nu minus nu dh. This is one of the expressions that we have already seen while discussing the essential concepts for solving these problems. And we know that this Ke max is related to the stopping potential as charge of the electron E times V suffix S is equal to H nu minus nu threshold. But here in the problem, the incident radiation uh, wavelength is given, not the frequency directly. So we can write based on C is equal to nu times lambda. That is, the speed of light is frequency times wavelength. So the speed of the electromagnetic radiation is uh, frequency times wavelength. So using this, we can say that um, for the wavelength, we can calculate the frequency, corresponding frequency as nu is equal to C over lambda. That is 3 times 10 power 8 meters per second is the speed of light over the lambda is 380 nanometers, so 380 times 10 power minus 9 meters. Right. So the lambda from the lambda 380 nanometers, the frequency turns out to be about 7.89 times 10 power 14 hertz. Right. Now we can write directly E times the stopping potential is H nu minus nu threshold, and H times nu is given. We have calculated now this as a value. Nu threshold is from the work function, we have worked out that to be 7.1 into 10 power 14 hertz, so we can use that here. So 7.89 times 10 power 14 minus 7.1 times 10 power 14, and this is 6.63 into 10 power minus 34. So if we plug in the numbers, here we get 0.79 times 10 power 14 hertz. So the final value for this is EVS, let's say, is equal to 5.23 times 10 power minus 20. The units are joules. This is energy units. We want the potential, stopping potential, so we have to divide that by this E. So 5.23 times 10 power minus 20 joule over 1.6 times 10 power minus 19. That's the charge of the electron. We would get the stopping potential to be around 0.33 volts. Right, let's move on to the next problem. A laser source of wavelength 532 nanometers emitting green light with a power of 2 milliwatt is shown on a photocathode having a work function of 1.95 eV If the efficiency of the photoelectric process is 10 power minus 5, calculate the photoelectric current in the circuit. So we have a source emitting a wavelength given. It is emitting green light of 532 nanometers and it has a power of 2 milliwatt. So the power is 2 times 10 power minus 3 watt. The wavelength lambda is 532 nanometers. And then efficiency is only 10 power minus 5. That means for every 10 power 5 photons that are incident on the target, the metal target or the metal surface, only one electron is ejected. This is what we mean by the efficiency in this process, right? So based on this, we can see that what is the photoelectric current we have to calculate. That means uh, for every 10 power 5 photons, one electron is ejected, and that would lead to photoelectric current. And what is the value of that current? So based on what is provided to us, first we can calculate the, and of course the work function of the photocathode, that is this particular uh, material, is given as 1.95 eV. Using these values, we should be able to calculate the current in the circuit. So first we have to see that how many photons are first incident on the target. That we have to calculate. So the number of photons is again a formula that we have used in the previous problems. That is the total energy, that is the total energy that is incident on the metal target over the energy of the photon, each photon. Right? This would be us to get the uh, so let's first calculate the total energy, this particular value. Let's call that E. This is made up of a number of photons, so we can say that E is equal to n times Hu. This n is what we need, right? So we see that this is the power that is given. So that means it is 2 milliwatt, that is 2 into 10 power minus 3 joule per second. That's the power. So we can say that the energy is equal to 2 into 10 power minus 3 joule per second by energy of each photon. That has to be calculated based on the wavelength that is provided, that is lambda is equal to 532 nanometers. So what is the energy of the photon, individual photon? E is equal to h times c over lambda. So if we plug in the numbers, that is 6.63 times 10 power minus 34 times 3 into 10 power 8 over 532 times 10 power minus 9. The energy of each photon, to work out these numbers, you will get as 3.74 times 10 power minus 19 joule, or in electron volt unit, if you divide this by 1.6 times 10 power minus 19, you will get as 2.34 eV. In this case, the power units are given as joules per second. So we can divide this directly with this particular value of energy, that is the energy in joule units directly. So we say that this is 3.74 times 10 power minus 90. If you do, then of course you will get N, isn't it? That is total energy, which is NH nu divided by H nu, which we have calculated here. This is equal to C by lambda, right? So that means N is equal to, if you do these numbers, uh, I'm getting something like 5.35 times 10 power 15 photons every second. That is the number of photons that is present in the instant light. Now, how to calculate the current? Out of all these photons, for each 10 power 5 photons, one electron is produced. For each 10 power 5 incident photons, only one electron is produced, but 10 power 15 photons are incident. So we can clearly see that based on the efficiency of 10 power minus 5 that is provided in this question, we can see that a value of n is equal to 5.35 into 10 power 15 photons every second gets converted to 5.35 into 10 power 10, right? Because of the efficiency of 10 power minus 5. Electrons every second, right? The efficiency is 10 power minus 5. So using this, we can calculate now the current easily, because each electron would contribute a charge of 1.6 into 10 power minus 19 coulomb, right? The electron charge, value of electron charge is this. So the current is, of course, the rate of flow of charge. So the current, let's say, is small I here. I is equal to 5.35 into 10 power 10 electrons per second times the charge of each electron. I multiply that here, and the resulting units are going to be, so this is just a number, right? Number times coulomb, but this is number per second here. So the resulting unit has to be coulomb per second, because we have multiplied the number per second by a charge. We get coulomb per second, and that is the current unit. So if you work out these numbers, we get current is equal to 8.56 times 10 power minus 9 amperes, right? So I is equal to 8.56 nanoampere, right? Nanoampere, you can say. That is the small current that we normally typically measure in photoelectric effect experiments, right? The human eye is sensitive to light source having as few as 100 photons. For an eye to detect orange light of wavelength 610 nanometers, how much energy is contained in the pulse? So the sensitivity of human eye is 100 photons only. Even if there are 100 photons in a light source, our eye is able to detect it. And the orange light, let's say in this case, is that is incident on an eye. The wavelength is given as 610 nanometers. So how much energy is contained in such a pulse? So basically for the given wavelength, E is equal to hc over lambda is the formula for calculation of the energy of the photon, and therefore 6.63 times 10 power minus 34 times 3 into 10 power 8 over the lambda is 610 times 10 power minus 9. If we work out the numbers, we get the energy of the photon to be 3.24 times 10 power minus 19 joule. Right. Of course, in electron volt units also we can write as 1.6. If we divide this is nearly 2 electron volt. Right? The conversion is division of this by 1.6 times 10 power minus 19 for conversion to EV units. Right. So this is energy of each photon present in the pulse of orange light. But for the eye to detect, we need 100 photons, so the energy must be at least 100 times this energy for detection. So the energy, how much energy is contained in the pulse? Energy contained in the pulse. Energy contained in the pulse is 2 eV times 100 such photons, so 100. If we multiply, we get 200 eV as the total energy contained in the pulse. Right. So let's move on to the next one. Right. The next one, the maximum speed of electrons released by tungsten target. So when light is incident on tungsten target, when light is incident on tungsten target, um, the maximum speed of the electrons that are emitted, that is given as, let's call that V max, 1.4 times 10 power 6 meters per second. What is the wavelength of the incident radiation? It is lambda. If the work function of tungsten metal is given as phi is equal to 4.63 eV. So based on this work function, we can get threshold wavelength, right? And then using that threshold wavelength and the incident wavelength, no, we have got maximum speed here, right? Speed. So we can get the kinetic energy from this, that maximum kinetic energy. So we have to use the expression Ke max, which is a photoelectric equation. Ke max is H times nu minus nu threshold. That's the equation. Of course, in terms of wavelength, we can write as Hc times 1 over lambda minus nu threshold can be written as 1 over lambda threshold here because C is taken outside, but typically we use something called lambda max as the notation for that, because nu threshold is defined as the minimum frequency, right? Minimum frequency. Whereas the lambda max is the maximum wavelength. Any wavelength greater than that wavelength, no photoelectric effect. Because when it comes to threshold frequency or minimum frequency, any frequency lower than that frequency will not produce photoelectric effect. Whereas when it comes to wavelength, in terms of wavelength, we say maximum wavelength, because any wavelength greater than that wavelength will not produce photoelectric effect. Of course, because of this relation, C is equal to nu times lambda. Therefore, nu is inversely proportional to lambda. And because of this, we call the frequency as either threshold frequency or minimum frequency. But wavelength, when it comes to this, we say that it is maximum wavelength lambda max. So here in the formula, we have therefore used the notation lambda max for it. Now using this, we can calculate, of course, kinetic energy max, Ke max can be written as half m v max squared. Of course, we have assumed a non-relativistic speed for the electron, and therefore we are using a classical kinetic energy expression of mv square max, and that should be sufficient for this particular case. Because the electron volt units we are dealing with for energy and all, so we can see that a non-relativistic expression is sufficient to deal with this. Right, now using these, we have been given 5. We can calculate lambda max from that. Lambda is also given to us. No, lambda is not given, so we have to calculate lambda based on the Vmax that is provided to us. So first, let me proceed to uh, so we need Hc over lambda, right? Phi is Hc over lambda max. If you take inside, that is the phi, right? So Hc over lambda max. And so based on these, we can write Hc over lambda is equal to the K max, right? So it is half m v max squared plus the work function, right? So this is like just K max plus phi is equal to Hc over lambda on the right side, right? Because the original equation K max is equal to Hc over lambda minus Hc over lambda max. So this is phi. So using this manipulation, we can write this like this. And therefore, we know the numbers, these numbers now. We can substitute these numbers because we know um, Vmax, we know the mass of the electron. Um, let's say, and we know phi as well, 4.63 eV. So that has to be converted into joule units. So phi is equal to 4.63 times 1.6 into 10 power minus 19. Then we can plug in directly these numbers because Vmax is provided to us in the question. Vmax is given as 1.4 into 10 power 6. That is the maximum velocity of electrons in this experiment. So plug in these numbers here on the right hand side. We have lambda on the left hand side which we need. So we can calculate lambda finally as lambda is equal to 0.5 for half, this half, times 9.11 times 10 power minus 31 kilograms for this mass of electron, and then Vmax squared. So this number that is 1.4 times 10 power 6 squared plus this one, that is 4.63 times 1.6 6 times 10 power minus 19 joule, and the entire thing this will be 1 by lambda. Let's say 1 over lambda is hc has been brought down here, right? That is divided by hc on both sides. You get this 1 over lambda expression. From there you can calculate lambda. H and c values are known to us, so we can calculate lambda based on that. So if I do that, let me write the lambda value here, final value. I'm getting 122 nanometers. That is the answer for this. If light of wavelength 400 nanometers and intensity 10 power minus 2 watts per meter square is incident on a potassium target of 5, 2.22 eV. The work function of potassium is 2.22 eV. Calculate the time lag between the incidence of light and the ejection of photoelectrons using classical considerations. So what do we mean by that? In the photoelectric theory, that is if Einstein's photoelectric theory, which is a quantum theory, there is no time lag between the incidence of light and the ejection of photoelectrons. This is quantum theory. But classically, please refer to the video lecture on the photoelectric effect in this channel. You would find that classically one can calculate a perceptible time lag between the incidence of light and the ejection of photoelectrons, and that is being asked here in this question. Based on classical considerations for the given situation, what would be the time lag? So that is the question for the given wavelength and intensity of radiation incident on the metal surface here, which is potassium. 2.2 eV is the work function given. Right, so first we can proceed to calculate the energy of the incident photon for a wavelength of 400 nanometers. So E is equal to Hc over lambda. Lambda is 400 nanometers. So I'm going to quickly plug in the numbers here. For H, for C is 3 into 10 power 8 over, for lambda it is 400 into 10 power minus 9. If you work out these numbers, you get energy of around 4.97 times 10 power minus 19 joule. This is the energy we're getting. Of course, we can convert it to EV units also if needed, but I think right now we'll keep it like that. And then we can see that the intensity is given as 10 power minus 2 watts per meter squared. So that is intensity, let's call that I, is equal to 10 power minus 2 watts per meter squared. That can be written as 10 power minus 2 joule per second per meter squared. Right? And therefore, we can say that in this case, on the metal surface, electrons are emitted by, let's say, the atoms on the metal surface. Because this is classical consideration, so we have to make some classical considerations in this case. We can't say that there is a Fermi sea of electrons in the metal, so on and so forth. Those are not classical considerations. Classical considerations means on the metal surface you could have atoms, and the light is incident on these atoms and electrons are ejected from these atoms. So we can consider typical radius of the atom let's say in this case, uh, to be about 1 angstrom, that is 10 power minus 10 meters. And how much total energy is falling on this particular atomic surface, we have to see, right? Uh, because this is the radius, one can calculate the area of the uh, a particular atom that is exposed to the radiation, incident light, that is. The cross-sectional area of that would be pi r squared, right? So using these, we can calculate the total energy falling on the uh, metal surface. That we can calculate because what is given here is intensity, right? So we can equate that to the total energy falling. So we can say that the total energy that must be falling, of course, it's a function of time over which the incident radiation is incident on the metal surface. So I say the total energy that is falling on the target is the intensity 10 power minus 2 uh, joule per second per meter square over an area. So I multiply that by area pi r squared over a period of time t. That is the total energy, right? Because we have power here over an area. So that area is the atomic area, and therefore, of course, the power is converted here by multiplying it over the duration. That gives you the energy units. From power to energy, this conversion has to be done. So that is multiplication over the time for which the energy is falling onto the metal surface. Of course, the r here refers to the radius of the atom, which we have taken to be about 1 angstrom. Now, using these numbers, we can get this total energy falling to be about 10 power minus 2 times pi times pi r squared. R squared is 10 power minus 10 whole squared, so that is 10 power minus 20 times t. Now, if this much energy is falling, that we can set it equal to the work function of the metal, because if that much energy is minimum falling, then that would emit, uh, that would cause the emission of a photoelectron. So we can say that we want time lag, right? Because once, let's say, a single photon, because we know from quantum considerations in terms of photons, so once a photon is incident on the metal surface, electron is ejected, but classically there is a time lag. Quantum theory predicts that there is no time lag, but classically there is a time lag, and therefore the time we have to take into consideration here. And this has to be equated to, therefore, the work function that is given for potassium, which is 2.2 eV. So we can equate these two numbers. 2.2 is the work function, so here that is the energy that is supplied to the metal surface. If you equate this and T is on one side, then we have 2.2 electron volt. This is in electron volt. So right side we have joule unit. So conversion of that is 1.6 into 10 power minus 90 joule over 10 power minus 2, 10 power minus 20, 10 power minus 22, 3.14 roughly for pi times 10 power minus 22. If you work out these numbers, you will get time of about 18.8 minutes. So that is a typical time lag that is calculated classically in photoelectric effect. But we know in real experiments of photoelectric effect, we don't see any time lag between the incidence of light and the emission of photoelectrons. Right. Let's move on to the next problem. The wavelengths of the visible spectrum range between 380 nanometers to 750 nanometers. What is the range of corresponding photon energies in electron volt units? What is the energy of a photon from an FM station if the broadcast frequency is 100 megahertz? So this is typical of a problem that we've done at the beginning. And then, but here there is a range of wavelengths that are given. So very simple calculations we can do to get to this. We know that the photon energy is given by in terms of wavelength h over lambda, and for 380 nanometers if you do that by substitution to you know, into this formula for lambda, we would get about 5.23 into 10 power minus 19 joule. Similarly, if you use the same formula for 750 nanometers and calculate the energy of a photon, you will get, of course, let's convert this into EV units, that is 3.27 EV. Similarly, here also 750 nanometers, we use this formula and calculate the energy, you will get in EV units as 1.66 EV. So, from the wavelengths, corresponding photon energies are given here. So this is typically the photon energies in photoelectric effect for the wavelengths that are used. That is 380 nanometers to 750. This typical range of 380 nanometers to 750 nanometers is the visible spectrum of the electromagnetic radiation. So the visible part happens to match with the typical work functions in metals, and that's why for photoelectric effect one can either use visible light or ultraviolet light to produce photoelectric effect. Right. Next is very simple. What is the energy of photon for the FM station? That energy is E is equal to H nu, that is 100 megahertz. So 6.63 into 10 power minus 34 times 100 megahertz, 10 power 6. So it is 10 power 8. This is 10 power minus 34. So the answer is 6.63 to 10 power minus 26 joules. That is energy. Of course, in UV units, you can write that as roughly about divided this by 1.6 into 10 power minus 19 to get it to UV units. That would be typically about that is something around 4 into 10 power minus 7 EV. So that is a very small frequency compared to visible spectral frequencies. So we can clearly see that the energies are very small. The energy of the FM station radio photons, radio waves, so they are very small, and we can therefore see that if you use radio waves, photoelectric effect will not happen because the metal work functions are in EV range, whereas the energy of photons in radio waves, they are typically at least 1,000,000 times less. So radio waves will not cause any photoelectric effect in metal surfaces. Typical energies are not sufficient. Right, let's move ahead to the next problem. Cesium's work function is given as 1.9 eV, of course, which is the lowest of any metal. What is the threshold frequency and maximum wavelength to eject a photoelectron from cesium? If the wavelength of light used is 300 nanometers and 400 nanometers. What would be the corresponding stopping potentials? Vs. Vs values we need. The first part is quite simple here. That is from this work function we have to calculate the threshold frequency, right? And lambda max. So let's say nu th, the threshold frequency, is equal to 5 over h. That is 1.9 EV, or 1.9 into 1.6 into 10 power minus 19 joule over 6.63 into 10 power minus 34. If you work out these numbers, you get 4.59 times 10 power 14 hertz. Right? Of course, lambda max you can calculate. Lambda max is equal to C over UTH. Because C is equal to nu lambda, we can use that and get it. So 3 into 10 power 8 over 4.59 into 10 power 40. This one if it work out, I would say this would be about this is 10 power minus 6 because numerator, this number if you plug in 3 over 4.5 and that would be about 0.654, let's say, into 10 power minus 6, or I can write this as 654 nanometers. Right, now that we have got these two numbers, that's the first part, that's done A. Threshold frequency is this, maximum wavelength lambda max is this. Now let's move on to the next part, that is if the wavelength of light used is these two values, what would be the corresponding stopping potentials? Two different stopping potentials have to be calculated based on the wavelengths that are provided to us. So for the first wavelength, let's say lambda is 300 nanometers. The stopping potential EVS expression for that is EVS is equal to Hc over lambda minus Hc over lambda max. Hc over lambda minus Hc over lambda max, we know that lambda is 300 nanometers in this case. Lambda max we have calculated in the previous step, so we have to plug in those numbers, and of course the electron charge can be at a later stage used commonly divided on both sides, let's say NKVS. So if I do that, first let me calculate the EVS part. If I plug in these numbers for those, I can take Hc out as well. So 6.63 into 10 power minus 34 times 3 into 10 power 8, 1 over lambda inside this thing, that is 300 into 10 power minus 9, minus 1 over lambda max, which we have calculated in the previous stage as 654 nanometers. So 654 times 10 power minus 9 there. EVS, if you do the math, you will get 3.58 times 10 power minus 28. That's what I'm getting. So Vs is 3.58 times 10 power minus 28 over 1.6 times 10 power minus 19. That would be 2.23 volts. That's the value I'm getting. Similarly, if one proceeds to do For the other lambda that is provided in this problem, that is for 400 nanometers, I'm not going to work out, I'm going to just provide the final answer. If you do the math, you would get Vs as 1.21 volt. So these are the values that are asked in the part B of the question. So we have done that. Let's proceed on to the next question. Will yellow light of wavelength 560 nanometer cause ejection of photoelectrons from molybdenum whose work function is 4.22 eV. So 4.22 eV 5 can it cause no, can this particular wavelength, for example 560 nanometers, can it cause ejection of photoelectrons from molybdenum whose work function is it's minus 9 on the right, nanometers, so meter, right? So can it cause uh, this thing, molybdenum, let's say here, light is incident of a particular wavelength lambda, but the work function we know has an expression phi is equal to hc over lambda max. If any wavelength higher than that value is incident in this case, no photoelectric effect, because when it comes to lambda it is max. When it comes to frequency it is minimum. So using this we can see that if I calculate lambda max for this particular case, my lambda max for molybdenum is equal to hc over 5, and that is 6.63 into 10 power minus 34 times 3 into 10 power 8 for hc over 5 is given as 4.22 in electron volt unit. So I'm converting that into joule units as 1.6 into 10 power minus 19 by multiplying here, and then I have to now work out these numbers. Lambda max is equal to 19.89 into 10 power minus 26 on the numerator, and here 4.22 times 1.66, that is 6.75, the denominator, times 10 power minus 19. So we can say that that is a 10 power minus 7 now on the numerator, and these numbers we have just 2 point lambda max is 2.95 into 10 power minus 7 meters, or I can write lambda max as 295 nanometers. Now the question is, can this wavelength cause photoelectric effect, is the question. This wavelength lambda max is 295, but the given wavelength is 560 nanometers, which is greater than lambda max. So I have to say that this will not cause photoelectric effect. That is the conclusion we can give. So I write here, since lambda, that is the incident electromagnetic radiation, the wavelength of incident electromagnetic radiation is greater than lambda max, yellow light will not cause any photoelectric effect in molybdenum. That is the question, right? Yellow light of wavelength 560 nanometers, can it cause photoelectric effect? No, it won't cause photoelectric effect in molybdenum. That is the answer. Let's move on to the next problem. If light of wavelength 653 nanometer is the longest wavelength that will cause emission of electrons from cesium, what is the work function? So 5 for cesium we have to calculate. In a previous problem we had used this value, so we know the value. It's not that we don't know we can look up even standard tables for that. But the question is that for a given lambda max, longest wavelength, 653 nanometers. What is the phi? So phi is equal to hc over lambda max. So if you substitute these numbers, in this case, you would get about 1.9 eV. That is the lowest for any metal. We have seen it in a previous problem. The lowest work function for any metal is for cesium, and that was given as 1.9 eV back then. So if you work out these numbers, you get the same value here. Right. So the part B of this question tells us that there is an ultraviolet light that is incident on cesium, which is 300 nanometers. Of course, that is less than lambda max here. You see, lambda is less than lambda max, so that should cause photoelectric effect. So what would be the energy of the ejected photoelectrons? That is maximum kinetic energy. That is what we can calculate from the photoelectric equation. So using the formula Ke max is equal to HTSC times 1 minus lambda, 1 over lambda rather, minus 1 over lambda max. Using this formula, we know the value of lambda here. We know the value of lambda max that's given here. And Hc is constant, we know that. So we can get Ku max using these substitutions. And I'm giving you the final answer in EV. If you work out these numbers, you get 2.24 EV. That is the final answer. Okay, let's move on to the next problem. The frequency range of radio waves is of the order of 1 to 100 megahertz. 1 to 100 megahertz. What is the range of energies of these photons? Our bodies are constantly bombarded by these photons. Aren't they dangerous to us? That's the question. Radio waves are everywhere now. We are using radio waves for transmission of electromagnetic signal and information through electromagnetic signals, that is radio waves, for transmission of radio signals, and for mobile phones. For all telecommunication purposes, radio waves are used. And are they not harmful to us? Aren't they dangerous to us? Our bodies are constantly bombarded by these photons. So the question is, for the given frequencies, we have to calculate the energy ranges and see that what effect it can have on human bodies, right? Right, so for 1 megahertz, if you calculate E is equal to h nu is photon energy, the formula for expression for photon energy. If you calculate that, 6.63 into 10 power minus 34 times 10 power 6, that is 6.63 into 10 power minus 28 joules. In EV, it is 6.63 into 10 power minus 28 over 1.6 into 10 power minus 19. This is going to be 10 power minus 9 EV. This is nearly 4.14 into 10 power minus 19 EV. That's a small energy. So for 100 megahertz next, if we calculate the same thing, it would be nothing but this multiplied by 100. So that is 4.14 times 10 power minus 7 EV. So these two values for a given range of frequencies of 1 megahertz and 100 megahertz are the values of energy, right? and they are very small. So even if our bodies are constantly bombarded by these photons, they cannot cause any damage to our cells in the body, right? The atoms in the cells will not be particularly excited by uh, these small energies. What I mean by that is that these energies are not sufficient enough to cause any kind of ionization effects in the cells in the human body, the atoms of the cells in the human body, and then therefore no radiation effects these low energies can cause. So basically, the energies are low. That's the reason why they are not dangerous to us. And so we keep using all these radio waves for all our communication purposes. Right. Let's move on to the next problem. Uh, Problem number 12. What is the longest wavelength that can cause photoelectric effect in aluminium? Aluminium, the work function is given as 4.08 eV. The lambda max is going to be Hc over 5, that is 6.63 into 10 power minus 34 for H, and 3 into 10 power 8 for C, over 4.08 times 1.6 into 10 power minus 19 for phi in joule units. So if you work out, you get lambda max 300 nanometers. That is the lambda max for aluminium. Right. Let's move on to the next one. The stopping potential is V when light of wavelength lambda illuminates a copper surface. What will be the stopping potential if the same wavelength is used to illuminate sodium surface? Wavelength is same in both cases, but these two metals have different work function values. Phi Cu, let's call that, and phi Na here. So what will be the stopping potential? Because the stopping potentials Vs for let's say copper is different from Vs for sodium, right? So what are the values? Let us call the stopping potential for copper, since we have two different metals here in this case, we can call the stopping potential for copper as Vs, let's say comma Cu in the suffix, and for sodium let's call that as Vs comma sodium Na here. Okay, and what is given here for these two surfaces, what is not given here is of course the work function values. And do we need those values here? Yes, we do need those values here because we have to write the photoelectric equation to solve this in terms of EVS. So let me write that first out. EVS comma Cu, let's say for the copper case, is equal to, in terms of wavelength we can write, or frequency we can write, but let's say lambda is given here, so we write in terms of wavelength. Therefore Hc 1 minus lambda minus 1 over lambda minus 1 over lambda max. In the same way here, EVS Na is equal to Hc 1 over lambda minus 1 over lambda max, but here lambda max is different for these two metals. So we can straight away if we write this equation, let's call this first equation 1 and let's call this 2. If we subtract these two equations. Let's call that to identify lambda max for copper as lambda max Cu, and here lambda max Na. Then we can manipulate these two equations. So if I subtract 1 and 2 from 1, let's say, I get EVS comma Cu minus EVS comma Na for the left hand side is equal to, on the right hand side same wavelength is used, that's what it's mentioned, right? So the lambdas are same here, this expression. So the first terms would, when I do the subtraction, first term would cancel out, and the second term has Hc as a common factor, so I take that out. 1 over lambda max Cu minus 1 over lambda max Na, that is the remaining thing that I have, right? So we can proceed here using this. So on the left side, the electron value, energy, the electron charge value is the same, and we have VSCU minus VSNA. That is the stopping potential of copper minus the stopping potential of sodium times E. The electron charge is on the left hand side. On the right hand side, we have we go and check here Hc lambda max Cu. So even if you don't take this Hc outside and you keep the Hc inside the square brackets, we get a phi of Cu minus phi of Na. That is what the expression equates to. So phi of Cu minus phi of Na, because phi is Hc over lambda max. So phi of Cu for copper and phi of Na for sodium. We have been given what? The stopping potential for copper in the question. If you see that, the stopping potential is V when lambda is eliminates copper surface. So in this particular case, this particular thing has to be taken as V. So E V minus Vs and A. Accordingly, we rewrite this. These two values are not provided, but from the tables we can get that for copper, phi is 2.28 eV, and for sodium it is 4.70 eV. These two values can be substituted here, and therefore the resulting would be a negative 2.42 eV on the right hand side. So in terms of V, we want to write the answer. So of course, these are in EV units. If you want to convert this to volt, we can write 2.42 volts. Of course, this electron charge need not be multiplied there. So that directly becomes Vs Na. So the stopping potential for sodium, if you take it to the right side and bring it here, we can write finally the stopping potential of sodium in terms of the stopping potential of copper, which is V in this case, is V plus 2.42 V. This is volt unit, so of course I have to write clearly that might cause some confusion, right? So this is this. So this is what is expected in this question, right? What is the stopping potential if the same wavelength is used to eliminate sodium sulfate? The stopping potential, therefore, for when sodium is used is if V is used for copper as a stopping, when copper is used, if V is the stopping potential, when sodium is used, the stopping potential would be about 2.42 volts higher. That is, of course, ba- based on the known values of the work functions for copper and sodium. Okay, so let's move on to the next problem. What is the stopping potential of when light of wavelength 220 nanometers is used to illuminate a surface of zinc whose work function is 4.31 eV? So for zinc, this is given. What is the maximum when light of wavelength 220 nanometers is used to illuminate? So we need to calculate the stopping potential in this case when lambda is given 220 nanometers and phi is given as 4.31 eV. So we can first proceed on to calculate lambda max using the phi value. Lambda max is equal to hc over phi. Phi should be converted to joule units from eV so that lambda max can be obtained in um, meters or nanometers as the case may be. So 288 nanometers, if you work out the numbers, is what you would get. And then the stopping potential Vs is hc over E, because EBS is equal to Hc times this. So if you bring the E there, it will be 1 over um, lambda used. Lambda used is 220 nanometers in this case, minus 1 over 288 nanometers. That is lambda max. So the wavelength that is used is must be less than the maximum wavelength. So that is also okay here. So if you plug in these numbers, these nanometers has to be converted into meters, so it is 10 power minus 9 in the denominator here opposed to numerator as 10 power 9 in these cases, so the nano part is no, above here. And then if you plug in these numbers, finally you get Vs as 1.33 volts. That is the answer to this question. So let's move on to the next problem. Calculate the frequency on wavelength of a 100 MeV photon. A 100 MeV photon energy is 100 MeV therefore. So 100 times 10 power 6 eV. What is a nu and lambda? That's the question. So this, if you convert into joule units, it is 1.6 into 10 power minus 11 joules, right? And therefore nu, if you want to get nu is E that is given over H, that is 1.6 into 10 power minus 11 over 6.63 into 10 power minus 34. So that would be, if you do the numbers, you will get 2.4 times 10 power 22 hertz. Very high frequency radiation. And then lambda, if you get, that is C over nu. You get about 1.25 times 10 power minus 14 meters. Right. Let's move on to the next one. If the conditions are favorable, the human eye can detect and light energy as low as 10 power minus 18 joules. So if light energy uh, is only 10 power minus 18 joules, even that is sufficient for the human eye to detect. How many 600 nanometer photons would this represent? The energy of the photon is given as no, we have to calculate that based on the wavelength that is given, that is 600 nanometers. And the total energy that can be taken as 10 power minus 18 because that is sufficient for the detection of the human eye. So energy of the photon, first let's calculate using this. E is equal to hc over lambda. If you substitute lambda as 600 nanometers, you would get the energy of the photon to be about 3.32 times 10 power minus 19 joules. And then this is 10 power 18. So number of photons should be the energy of the radiation that human eye can detect, the minimum energy, let's say, over the energy of a photon that it contains. That is, so that number would be in the range of about 3 photons only, right? Because you have 10 power minus 18, 10 power minus 19, so it is 1 over 3.32 in that case. That would be about 0.3 joules, roughly 3 photons. So the human eye is so sensitive to light, it can even detect 3 photons. Right. Let's move on to the next problem. In a surgery of the eye, a detached retina is being welded back in place using 20 millisecond pulses from a zero point 0.5 watt laser operating at 632 nanometers. How many photons are there in each pulse? No, we know that the laser can be used for eye surgeries to correct, retinal deformities or issues with retina. So the retina is being welded back in place using a laser source of 632 nanometer wavelength, and the energy of the source is 0.5 watt, but it is a 20 millisecond pulse laser that has to be taken into account. And therefore, how many photons are there in this laser uh, pulse, in each pulse of this laser? B, right? So first, number of photons, of course, we know we can calculate from total energy. If we know the energy of each photon, so energy of each photon for the given wavelength we can calculate. E is equal to hc over lambda. If you substitute this lambda, you would find that it is about 3.15 times 10 power minus 19 joules. And then if you use that for this 0.5 joules per second, this power is watt here, so that number of photons, if I calculate, is equal to 0.5 joule per second over the energy of this each photon, that is 3.15 into 10 power minus 19. That should give you number of photons, but that is not the case here, simply because it is not a normal continuous laser. It is a pulsed laser of 20 millisecond uh, pulse duration, and therefore that has to be multiplied onto the numerator. So that is 20 milliseconds. So I'm using a 10 power minus 3 here on the numerator for milli. So these numbers are worked out. They get the total number of photons as 3.2 into 10 power 16 photons. This is the number of photons that are present in each pulse of that pulsed laser of 0.5 watt 20 millisecond pulses that is used in this retinal correction surgery. Right. Let's move on to the next problem. The threshold frequency of copper is 1.1 into 10 power 15 Hertz. When a light of frequency 1.5 into 10 power 15 Hertz is incident upon the copper surface, what is the maximum kinetic energy of the ejected photoelectrons? So we know that the threshold frequency of copper here is this, and then the incident frequency is given as maximum kinetic energy is a very simple calculation, right? So Ke max is equal to h times nu minus nu threshold. So the difference here is straight away zero point 0.4 times 10 power 15 times this. So 6.63 into 10 power minus 34 times zero point 0.4 times 10 power 15. If you do the numbers, you get EV 1.66 EV. That's the answer you get. Let's move on to the next one. A sphere made of silver is suspended by a string in a vacuum chamber. What is the electric potential acquired by the sphere when ultraviolet light of wavelength 200 nanometers is directed at it? So we have a vacuum chamber, let's say, and then inside this vacuum chamber, uh, let's say a string is used to hang up a silver sphere or a sphere made of silver, and then maybe through a small uh, window, let's say here, right? Light is incident on this. That wavelength is given as 200 nanometers. What is the electric potential acquired by the sphere? So here, this is also an application of photoelectric effect. This is ultraviolet light that is incident on this metal surface, and that should cause some ejection of photoelectrons from this metal surface. And as a result, the metal surface will acquire some electric potential. So we can calculate the energy of the incident photon using the expression Hc over lambda for the given lambda of 200 nanometers. If we do that, we will get about 6.22 eV. That's the first stage, right? That is 6.22 eV. Now for silver, phi is about 4.7 eV. I'll look up the tables for this. And therefore the kinetic energy of the electrons, the maximum kinetic energy of the electrons that are ejected in this process would be the energy of the incident photon, that is 6.22 eV, minus the work function. That would be about 1.52 eV, right? 1.52. And therefore, the electric potential that is acquired by the metal sphere must be around 1.2 volts. That is the answer. So V is equal to, let's say that is the potential of electric potential of silver, in this case 1.52 volts. That is the answer to this question. Next is when a light of wavelength 400 nanometers is shown on a metal surface of a function 2.5 eV. What is the stopping potential at which photocurrent disappears? Of course, the idea of stopping potential is that is the potential at which the photocurrent becomes zero. So, what is the speed of the fastest photoelectrons? V max is what is asked. This question. Lambda is given, phi is given, so we can calculate kinetic energy max. K max. If we can calculate from that, we can get V max, because K max is equal to half m V max squared. So For Vmax, we have to get Kemax. For Kemax, we have the photoelectric equation, that is Hc times 1 over lambda minus 1 over lambda max. And here lambda is 400 nanometers. Lambda max we have to calculate from the work function, because phi work function is equal to Hc over lambda max. So if you do this, lambda max you get as no, you don't have to even do that actually. Why? Because we can calculate this into EV and then do the simple subtraction. That would be better. So lambda, if you take as 400 and calculate that energy, Hc over lambda, for lambda is equal to 400 nanometers. Hc over lambda, if you calculate, that would be around 3.11 eV. That is the first term here. This. So K max, therefore, which is on the left hand side here, K max is equal to 3.11 eV minus, of course, this Hc over lambda max. This is work function phi, which is given as 2.5, so 2.5 eV. So simple application of the photoelectric equation gives us K max. K max is 0.61 eV, therefore. If you know the K max, then half mv square max we can use and calculate the speed of the electrons. So half mv max squared is 0.61 eV, and therefore Vmax squared is equal to 2 times 0.61 from this, 2 times 0.61 eV over m, that is the mass of the electron, 9.11 into 10 power minus 31 kg. Of course, this eV has to be converted to joule units to do this calculation. So this is what we get. And if you do this math, you would get about 0.214 times 10 power 12. That is the units for V max squared, that is meter squared per second squared. From there, V max is, by taking a square root for this, we get 0.46, let's say, times 10 power 6 meters per second. This is the speed, maximum speed of the photoelectrons ejected in this process. That's the answer. Calculate the Planck's constant from the data provided. The work function of tungsten surface is 5.4 eV. The wavelength of light source is 175 nanometers. The maximum kinetic energy of the ejected photoelectrons is 1.7 eV. So we have to calculate the Planck's constant in this particular case. The work function for tungsten is 5.4 eV. The wavelength lambda is 175 nanometers. The Ke max is given as 1.7. We know that Ke max is equal to the energy of the incident photon minus the work function. So h nu is Ke max plus 5. So h nu is the energy of the incident photon. Ke max is given as 1.747 eV, and then this is 5 for tungsten. That is given as 5.4 eV. So in eV units, if we work out, it is 6.47.1 eV for h nu. What is asked is the Planck's constant. So H is equal to 7.1 EV, or 7.1 into 1.6 into 10 power minus 90 joule over uh, nu. Nu is C over lambda, and that is given as 175 nanometer lambda is. So C is 3 into 10 power 8 over lambda, that goes to the numerator as 175 nanometers. 10 power minus 9, I'm multiplying there. So if you work out these numbers, since it's Planck's constant, I'm just kind of doing uh, more steps here. 10 power minus 8 goes to the numerator as 10 power plus 8, and the denominator goes to numerator as 10 power minus 8. There is a minus 19, there is minus 27, there is a minus 9, that is 10 power minus 36. So we have 7.1 into 1.6 times 10 power minus 36 on the numerator times 3, the denominator, that is 3 here, times 175 is still there. So 7.1 times 1.6 times 175 is 1988 by 3 times 10 power minus 36. We get for this 662.66 times 10 power minus 36. That is the value for this expression, and that can be written as 6.63 roughly times 10 power minus 34 root second units for Planck. So we get a very accurate value of Planck's constant for given data. Right, so that is the part 1 of the problems on the photoelectric effect. Please do look out for the part 2 of the video as well on the same topic, that is solving problems on the photoelectric effect. Thank you.